Let's discuss how the BJT or bipolar junction transistor works. Alright, the BJT is basically a three-terminal device made from a single crystal semiconductor, generally silicon. It's very much like your PN junction. Okay, so if you recall your PN junction, okay, you have a P and an N material here. Okay, and basically what happens is the P is positively charged and is negatively charged. Okay, in terms of the doping, and when you place them together, we know that it creates a barrier. Okay, and then to overcome that barrier, there is a voltage of 0.7 volts that it needs to overcome. Okay, so the PN junction, if you were to draw it, okay, it looks something like this. P and N, and when they are initially fused together, they create that barrier, okay, where there is a crossover of P particles to the N particles to the P. All right. For a transistor is basically an extension of the idea, where instead of just two materials, you fuse three different materials together: emitter, base, and collector. Okay, that's what we call them. All right, and we are basically focusing on what we call the NPN BJT. Okay, the NPN BJT. Uh, and so what we are going to do here is we're going to fuse three materials together: N, P, and N. Okay, and the way they are called, okay, is the base. The center of it is called the base. Okay, so this is the base. Then on one side, where it is more heavily doped, as you can see here, N++, we call it the emitter. And the other side, which is also N, okay, but it's a bit lesser doped, we call it the collector. Okay, in terms of the symbol, okay, this is how the symbol looks like. So in schematics and circuits, circuit diagrams, you probably see this as a symbol for the BJT. Okay, the BJT can be operated in a few different ways. The one we are going to be focusing on in this video is the amplification mode. Okay, and that is to basically look at how a transistor can be actually used to amplify signals. Okay, we also know that op amps can be used to provide amplification, and transistors are also another device we can use to provide a kind of amplification that we want. Okay, and in order to amplify a signal, we need to operate that device or the transistor in the forward active region. Okay, so there are four main regions. The cutoff is when it's not functional, okay, it's not working, okay, or we call it the off state. The forward active region is where there is an amplification mode of the device, okay, where I can provide an input signal, and at the output side I get the amplified version of it. All right, so that is what we're going to be focusing on in this video. In terms of connecting up a circuit, okay, for the transistor, what you need is you need to provide two voltages. One is at the base, okay, to bias the base and emitter junction over here, and the other is of course across the collector and emitter over here. Okay, and in order for the device to work, okay, the amplification part, okay, that we are focusing on is the current that we provide at the input side, which is the base, and the current that we are able to extract out at the emitter and the collector side over here. Okay, so the base is considered like the input to the device, and the output is either at the collector or emitter, where we have the amplified signal. Okay, now let's see how we can analyze a simple circuit using two different approaches. Okay, before that, let me just quickly show you the formulas associated with the transistor. We can say that the IC, the collector current, is beta IB. Okay, and beta is the amplification factor. Okay, and this amplification factor of beta can easily be a high value. In our example, we're going to say it's 100, but it depends on the transistor and the configuration in which we are using it. Okay, so the beta is a amplification value which is a high number. As you can see here, with beta being a high number, it is quite clear that whatever base current you have, it will be amplified by a large amount, and that amplified current is what the collector would see. Okay, so that is why I said that the base is considered the input, and whatever you see at the collector and the emitter is the output, the amplified current. Okay, so besides this formula, you also have a few other formulas. IC equals to alpha IE, and alpha, okay, is given as beta over beta plus 1. So you can see that beta or beta plus 1 is approximately 1, correct? So in some cases, you can say the IC is almost equivalent to IE, okay? And of course, by rearranging some these formulas, you can also get another relationship that IE is equals to beta plus 1 IB. All right, so these are the formulas associated with the uh, transistor. Okay, and now we're just going to do a simple analysis of the transistor using the Thevenin equivalent approach. Okay, so in this circuit, what we have is we have a transistor here, and we have connected two resistors on the base side, or the base to the base terminal in this configuration. And at the same time, we have a resistor at the collector terminal, and the emitter is directly connected to ground. Okay, for Thevenin equivalent circuit, what we need to do is we first need to understand that the Thevenin part is the conversion of the input to the system. Okay, and the input is the base. Okay, so what I need to do is I need to look at this portion here, which is the base portion of the circuit, and derive a equivalent Thevenin circuit if I look from this direction here. So if I just look at that, what do I see? Okay, I will see that the uh, I will get a voltage of 10 volts, okay, to a resistor here 600k, okay, and this is the junction, the base junction here, and another resistor of 300k here. All right, so this is the point at which I am looking at, okay, to get the Thevenin equivalent circuit. In order for me to get the Thevenin resistance, what must I do? Okay, if you recall back your approach for Thevenin conversion, to get the Thevenin resistance, the voltage source must be replaced with a short circuit here. So that effectively means that the RTH here, if I look from this direction, RTH is basically 300k parallel with 600k, correct? And that will give me 200k. All right, so that is for the RTH portion. Okay, now let's go back and see the VTH. So for the VTH, I put back my 10 volt source here. So I got 10 volts here. And the VTH is basically the voltage that I see across when I look from this direction. So when I look from this direction, I only see a simple circuit, which is a voltage and two resistors in series. Okay, so the Thevenin voltage is basically the voltage that you see across this resistor here. Alright, so the VTH is given as 300k over 300k plus 600k multiplied by the supply voltage of 10. Okay, and that will give me 3.33 volts. Alright, so basically now you have converted the input of the circuit, which is connected to the base, you have converted it and created a Thevenin equivalent circuit. Okay, now what is the next step? The next step is to redraw the circuit with its Thevenin equivalent. So the Thevenin equivalent voltage is now 3.33 volts, okay, and that is passing through a Thevenin resistance RTH, which is equals to 200k. And what I'm going to do is, so this uh, part of the circuit here has been converted to look like this, correct? A Thevenin equivalent. And now what I'm going to do is I'm going to draw the transistor, but in a slightly different way. Okay. As we said earlier, the base and emitter is equivalent to saying that it is a PN junction. So this PN junction, base and emitter, in order for it to be functioning in the forward active region, the VBE must be greater than 0. Okay, so you think of this as just a uh, one a diode okay, extracted out from a transistor. Okay, so for the uh, for the forward active region, VBE must be greater than 0 in order for it to be functioning. Okay, for VBE to be greater than 0, that means I want current to be flowing in this direction. That means from a diode perspective, the moment a diode starts to conduct current in the forward bias approach, we know that the voltage across the diode is fixed at 0.7 volts, correct? Okay, so that is what we know from the learning of the diodes principles. So we can say that there is always going to be a 0.7 volts drop across the base emitter junction. So this is the base, okay, and over here at the emitter, there is going to be a 0.7 volts. All right, and the emitter is directly connected to ground over here, so it's directly connected to ground. Okay, and over here is the collector, and as we have seen in the formula here, IC is given as beta IB. So the current that is going to flow through from the collector side, okay, is actually a amplified current. So this is beta IB. Okay, and this is actually your collector over here. Okay, and over at the collector side, you still have a 3K resistor pulled up to ground. Okay, so let me use the same color here. 3K resistor pulled up to 10 volts. Okay, sorry. All right, so that is what you have over here. Okay, so what I've done is I've converted this circuit here and the original Thevenin equivalent circuit, the original circuit to a Thevenin equivalent circuit. Okay, and at the same time, I've also converted the transistor to a representation that shows the 0.7 volts drop across the base and emitter, and at the same time the amplified current that is going to flow through the collector terminal. All right, so now that we have this equivalent representation, what we can do is we can start with our analysis. All right, so what can we see now? We can see that so maybe let me draw this properly. There's a ground here. So over here there is actually input path for current to flow. Okay, so this is the input side of the circuit, and current will flow in this direction from the supply down to ground. Correct, so we can say that this current here, IB, okay, this current IB is equivalent to 3.33 minus 0.7, because this is the voltage drop here, and there's only one resistor which is 200k. Right, so that will be equal to 0.0132 milliampere. All right, so once I find IB, I can also find IC, correct? Okay, so IC in this case is equals to beta IB, which is, okay, so for this example, beta is given as 100, so it's 100 times 0.0132, which is equals to 1.32 milliampere. Okay, and if I find IC, I can also find IE. So IE is equals to beta plus 1 of IB, which is 101 times 0.0132, which is 1.33 milliampere. Okay, and with that I can also say I can also find what is VC. So VC is given as so before I go on to VC, we can see that right now I have already solved for all three currents. Correct, I can solve all three currents, IB, IC and IE, and as you can see, the current in IC and IE is a lot more amplified compared to the current in the IB. So that is the amplification factor of it. All right, so what is VC over here? Let me just complete that. VC is 10 volts minus, so over here you can see there's current flowing in this direction down to ground, so its VC is 10 minus 3k multiplied by IC, which is 1.32 milliampere, which is equal to around 6.04 volts. Okay, so that is basically the voltages and currents that you need to solve for this circuit. In order for us to confirm that it is actually in the forward active region, we need to make sure that two conditions are satisfied. VBE must be greater than 0 and VBC must be less than 0. So let's confirm that. Okay, so you can see that the voltage here VB, okay, the voltage here VB is equivalent to VB. So VBE is VB minus VE, which is the voltage from here to here. And since there is nothing else over here, it is VB to ground, which is 0.7 volts, which is forward bias. So that is the first condition fulfilled. And we want VBC to be negative. So let's calculate VBC. VBC is VB minus BC, which is 0.7 minus 6.04, which is negative 5.34 volts, which means it is reverse bias. So second condition fulfilled. So since both these conditions have been fulfilled, okay, VBE is greater than 0 and VBC less than 0, we can say that this transistor configured in this particular circuit is behaving or is configured to operate in the forward active region. Okay, that means it is designed for amplification purposes. Alright, so I hope with this analysis you get a clear picture of how to do the Thevenin equivalent circuit approach. Okay, and now I'm going to show you the voltage divider approach. Okay, so we have a slightly different circuit over here. Alright, and I'm just going to put in the values, okay, for these various components here. R1 is 20k, okay, R2 is 3k, RE is 1k, and this is 5k. Okay, and beta is 100. Alright, so write that properly over here. Beta is 100. Alright, so right now what we're going to do is we're going to approach the same circuit but with a voltage divider method approach. Alright, now from what we know, okay, we can say that IB is a very small current. Okay, it's in a microampere range, and if IB, okay, is going to be very much lesser than the current flowing through here. Okay, so we can call this current, okay, IR1 and IR2, because it's the same current flowing in. So rightfully, of course, when the current flows through here at this junction, it's supposed to split. Okay, but if we go by the understanding that IB is very small, so most of the current that flows to IR1 is also going to flow through IR2. Okay, okay, so it's much lesser than IR1 or IR2. So with this understanding, what we can do is we can say that IR1 is approximately equals to IR2, which is approximately equals to VCC. So VCC here is given as 20 volts, 20 over R1 plus R2, which is 20 over 20k plus 3k, which is equals to 0.87 milliampere. Alright, now once I know IR1, IR2, I can calculate the voltage over here, VB. Okay, so I can say that the voltage VB is equals to R2 over R1 plus R2 multiplied by VCC. Is basically a voltage divider rule, correct? Because now we do not consider any current flowing inside here. So it is 3 over 23 times 20, which is 2.61 volts. Alright, now what is the next step? Since I know VB, and in order for my device to operate in the forward active region, there will be a voltage drop of 0.7 volts here, correct? So we can say that VE is equals to 2.61, which is VB, minus 0.7, which is 1.91 volts. And once I know the voltage here VE, I can know the current flowing through this resistor RE, correct, which is IE. Alright, so let's calculate that. So IE is equals to VE over RE, which is 1.91 over 1k equals to 1.91 milliampere. Alright, now what is the next step? If I know IE, okay, I can find IC. Correct, so I can find IC now. I can say the IC is equals to beta over beta plus 1 of IE. Okay, so you can look back at the formulas that we went through just now, which is equivalent to 100 over 101 times 1.91 milliampere, which is equals to 1.89 milliampere. Okay, now that we have IC, we can now work back to IB. Okay, IB is equals to IC over beta. Okay, so IC is beta IB, so IB is IC over beta, which is now 0.0189 milliampere, which is 18.9 microamperes. Alright, so you can see that with the voltage divider rule approach, okay, as starting off with this assumption over here, okay, we can actually solve the circuit, okay, and still get our answers without going through the Thevenin approach. Alright, so the last step is of course to calculate VC, and then we want to confirm that it's in the forward bias region. So VC is VCC minus ICRC. Okay, why? Because voltage at this point is the VCC minus the voltage drop across RC. So that will be equals to 20 minus 18.9 milliampere multiplied by the 5k resistor. That will give me 10.55 volts. Alright, so now in order to confirm that we are in the forward bias, forward active region, we must confirm VBC first. VBC is VB minus VC, and VB just now was 2.61 volts minus 10.55 volts, which is negative 7.94, which is reverse bias. So one condition satisfied. The next condition is VBE must be positive, which is VB minus VE, which is 2.61 minus 1.91, and that is 0.7 volts. That is forward bias. So both conditions satisfied. Alright, so you can see that we can solve, okay, the different circuits using different approaches. One is the voltage divider method approach, okay, which is shown here. The second is the Thevenin equivalent analysis that is shown here. Alright, so with this video and examples, I hope you have a good understanding of how the BJT transistor can be used for basic amplification purposes. Alright, thank you.